Hello everyone and welcome to another Würth Elektronik webinar. My name is Son and I will moderate this webinar today. We are very pleased that you took the time to participate in our webinar. The topic of today is galvanically isolated voltage measurement made easy with digital isolators. Our speaker today is Artem Belyakov. Artem, hi, cool to have you here.
Thank you.
He will hold the presentation and then he will answer your questions. So now I give over to Artem and I wish you an exciting webinar.
Thank you, Lotsovas. Thank you for introduction. Thank you, dear colleagues, that you found time to join our webinar. And as you already know, today we are going to discuss about digital isolators. And I divided my presentation into three topics. The first topics will be about our new design for galvanically isolated voltage measurement. Second topic will be about the most critical properties of digital isolators. And the last topic will be about our about Würth Elektronik portfolio. But first, let me show you the main fields of application for digital isolators. There are, let's say, three big groups of applications, and the first group is industrial automation, where a lot of communication interfaces are used. For example, RS, CAN, SPI, I2C, and so on. The second group, solar and industrial power supplies. And the last, but of course not least, the third big group, electric vehicles and smart electric meters. These slides shows a good example of signal isolation. This is warehouse logistic. This is, let's say, a common place for strong magnetic fields, for AMI noises, and so on, because of many power devices or power machine are located here. For example, let me show you. For example, frequency converter, fan motor, and conveyor belt. All physical properties like current, voltage, temperature are measured by sensors in the field, and after that forwarded to central control unit. But the main problem is that the distance between sensors and sensor control unit can reach several hundred meters. And it means long wires, long lines, and that means a large parasitic capacitance and inductance that can affect signal integrity in this communication part of the system. And in this case, that's why isolated is required for preventing ground potential differences and for organization reliable data transfer. And in our opinion, digital isolators will be the best solution for this task. And to prove this point, we designed a reference example for galvanically isolated voltage measurement. As you can see on this slide, the design is divided into two boards, a transceiver and receiver, that can detect a DC voltage of plus minus 30 volts maximum. Both parts, the transceiver and the receiver, are galvanically isolated. The signal is transmitted between the transceiver and the receiver via a twisted pair cable. The length of this cable can be several hundred meters, depending on the electromagnetic environment. On this slide, you can see the transceiver board, and the transceiver circuit has 6 functional blocks. The first block is a probe with voltage divider and amplifier for measuring positive and negative polarity. Then level shifter for the voltage frequency converter. Digital output signal of the converter frequency depended on the input voltage. Then you can see digital isolator for galvanic isolation between measuring voltage and input part of the interface. Then goes buffer or interface buffer. This is a low impedance line driver with balanced output. And finally, you can see the block 6, the isolated DC-DC converter for the power supply of this transceiver board. The transceiver part or the transceiver board consists of 5 functional blocks. You can see here buffer again, then digital isolator and a frequency to voltage converter that generates an output voltage from a digital input signal. And the output voltage level depends on the frequency of the input signal. Then you can see a polarity indicator and signal amplifier. Polarity indicator shows polarity of input voltage. And again, the section number 5, this is isolated DC-DC converter for the power supply of the receiver board. The graph here shows the relation between the measured voltage or input voltage and the voltage that is then displayed at the output. The transmission characteristic is almost linear over the entire input voltage range from minus 30 to 30 volt, and it proves that our solution is suitable for electrically isolated data acquisition and data transmission. If you would like to know more about this reference design, you can read our application note or the article which was published in Elektronik Praxis magazine. The links you can see on this slide. Now let's discuss about EMI measurement for considered boards. As you can see on this slide, in the middle of the slide, there is the digital isolator that provides galvanic isolation between input and output that also has some parasitic coupling capacitance that can be sources of common mode interference. Usually, a design engineer uses some external Y capacitor for common mode noise reduction. But we would like to recommend you, or we would like to show you another approach. And instead of the external Y capacitor, we used the parasitic capacitance between the board layers as Y cap. This method is generally known, or this approach, known as stitching capacitance. This slide shows the receiver board. The Y capacitor is realized here by the parasitic capacitance between different ground layers, as you can see here in this picture. The area here, the area of 4-layer board is 77 by 50 millimeter, creating a parasitic capacitance of approximately 1 nanofarad, which is used as Y capacitor. The radiated emission measurement shows that we are well below the required limits. It proves that our approach with stitching capacitance works well. Also, on this slide shows the comparison between a radiated measurement of 2-layer board without external Y capacitor in this picture, and 4-layer board with 1 nanofarad parasitic capacitance as a Y capacitor. You can see it here. Okay. As you can see, the 2-layer board significantly exceeds the specified limits and does not comply with current standards. And the 4-layer board is well below the required limits. In our datasheet for 4-channel digital isolators with integrated DC-DC converter, you can find all necessary information about layers design optimized in terms of AMC, and also useful information about components for input and output filters of integrated DC-DC converter. Now that we already discussed the application of digital isolators, let's look at the most critical characteristics or properties of this product. There are, let's say, the main properties of digital isolators. I mean safety standards, clearance and creepage distance, comparative tracking index, data rate, propagation delay, default output state, current consumption, common mode transient immunity, and electrostatic discharge. But first, let's start with safety standards, because when we speak about digital isolators, we speak about safety, and safety standards are very, very important for Würth products. The main safety standards, you can see the main standards, or you will see the main standards on these slides. The first standard is UL 1577 from US. This is standard for optocouplers, but digital isolator can be also certified according to UL 1577 standard. Second standard is IEC 60747-17. This is the first international standard for digital isolators, and this is the most modern standard which allows to use digital isolators in the most critical application. And the last standard on the slide, this is VDE 0884-17. This is German version of international IEC standard, and they both are equal. Let's go next. And according to UL 1577, as certified devices, isolation barrier must withstand a certain level of RMS AC voltage or VISO for 60 seconds. At the same time, a digital isolator must withstand an isolation test voltage of 1.2 times VISO for 1 second. And in the table, you can see the isolation voltage level according to UL 1577 standard for Würth Elektronik's digital isolator. For SOIC 8 narrow body package, the isolation voltage is 3.75 kilovolt RMS. And 5 kilovolt RMS for SOIC 8 wide body and SOIC 16 wide body packages. IC or VD standard, doesn't matter, they both are equal, include 4 main isolation voltage. And you can see them on the slide. This is maximum working isolation voltage, maximum repetitive peak isolation voltage, maximum transient isolation voltage, and maximum surge isolation voltage. Maximum working and maximum repetitive peak isolation voltages. This is voltages that can be applied to the isolation barrier continuously over the lifetime of a digital isolator without reduction its functionality. Maximum transient isolation voltage. This is the maximum peak voltage that can be applied to the isolation barrier for 60 seconds. And this isolation voltage defined as a peak voltage. And sorry, I forgot to say that maximum working isolation voltage defined as RMS or DC voltage, and maximum repetitive peak isolation voltage defined as a peak value. And the last isolation voltage on this slide, it's maximum surge isolation voltage. This is the maximum instantaneous value of a voltage pulse that an isolator can tolerate, and this isolation voltage defined as a peak value. On this slide, you can see different levels of isolation. First of all, of course, it's functional isolation, which provides only necessary isolation for the correct operation of the system and doesn't protect against electric shock. Then, basic isolation provides protection against electric shock in addition to functional isolation. And compared to an isolator that provides basic isolation, an isolator that provides reinforced isolation has higher test voltage requirements. But of course you can ask what means a higher test voltage requirement. And the answer you can find in this table. You can see I specify a real example for real Würth Elektronik products. We have digital isolators in SOC 8 narrow-body package which provide basic isolation, and maximum surge isolation voltage for this product is 5000 volt peak. And also we have products in SOC 8 wide body and SOC 16 wide body packages. It means that those packages are wider than previous SOC 8 narrow body package, and those products provide reinforced isolation with maximum source isolation voltage 7000 volt peak. But if you check test voltage for basic isolation, you can see that test voltage is 1.3 times of maximum surge isolation voltage, and for reinforced isolation, the test voltage is 1.6 times of a maximum surge isolation voltage. And for basic isolation, the test voltage will be 6.5 kilovolt, and for reinforced isolation products, test voltage will be 11.3 kilovolt. And according to IEC or VDE standard, the minimum surge voltage for reinforced isolation should be greater than 10 kilovolt. And also, it's very important to know and understand that failure rate over lifetime for products with basic isolation should be less than 1000 ppm, and for reinforced isolation products, it should be less than 1 ppm. If you would like to know more about our safety certificates, please check UL website, and please use our certificate number, and you can see our safety documents for our digital isolators, and the same story for VDE certification. We have two certificate numbers for reinforced and for basic isolation. Okay, when we talk about safety, we cannot forget about clearance and creepage distance, because clearance and creepage distance are closely related to isolation voltage and play an important role in preventing arcing and ensuring the safety of the isolator. As you can see here, creepage is a shorter distance across the surface of the package between two conductive parts of an isolator. And the clearance is a shorter distance across through air between input and output terminals and isolators. And creepage and clearance distance for Würth Elektronik isolators in a SOC 8 narrow body package is 4 mm. And 8 mm for SOC 8 wide body and SOC 16 wide body packages. In addition to clearance and creepage distance, a package technology and the quality of the molding compound affect the isolation rating. Comparative cracking index indicates the OCTI, indicates the ability of the package mold compound to withstand constant high voltage stress without surface degradation. A higher CTI means a smaller package, it means smaller creepage distance for the same operating voltage. In this table you can see different material groups, and the Würth Elektronik digital isolators provide CTI of more than 600 volt RMS and correspond to the first material group. For digital isolators, are important not only to provide the necessary level of galvanic isolation, but also to ensure reliable transmission of high-speed data. As a result, the timing characteristic of isolators, such as data rate or propagation delay, are just as important as their isolation property. Data rate is the number of bits transmitted per second, or the fastest speed at which data can pass through the device. On this slide, you can see the most popular interfaces on the market, like RS-232, RS-422, RS-485, different types of CAN interfaces, I2C interface, and SPI interface. You also can see here the maximum data rate for the current interfaces. The internal structure of Würth electronic capacitive digital isolators is shown on this slide. Digital isolators transmit signals across an isolation barrier, and this achieved by using a modulator to transmit high-frequency signal through the isolation. You can see high-frequency modulator here. Propagation delay is the same time it takes for a digital signal to pass through the internal structure of a digital isolator from input to output. You can see in this picture the input signal, high-frequency signal across isolation barrier, and then you can see some output signals. Of course, between input we can see some delay between input and output, and of course for high-speed applications this delay should be as small as possible. Also, you can see in this table that propagation delay of Würth Electronics digital isolators is between 15 and 20 nanoseconds. And also you can see here channel-to-channel output skew time. This is a time delay deviation between different channels of the same digital isolator. And also you can see here part-to-part output skew time. And this is a time delay deviation between digital isolators of the same type. Another very important property is a default output state. Default output state is a predefined state of the output signal pin when the input side of the isolator is not powered. Is not powered or the input signal pins are open. Digital isolator can provide default output state high or default output state low. Selecting the right digital isolator depends on the specific application, and before describing this application, it's necessary to understand the differences in the operation of digital isolators with different default output states. Let's start with default output state low, and you can see the diagrams here on this picture. And for default output stay low, the modulator of the digital isolator transmits high-frequency signals through the isolation barrier only when the input has a high signal level. Again, we can see high level of input signal here, and only during this period, during this time, internal high-frequency modulator works. Then, and vice versa, the modulator of the digital isolator with high default output state transmits high-frequency signals through the isolation barrier only when the input has a low signal level. Again, we can see here that when the input is low, only during this time the internal high-frequency modulator works. Now speak about application. Of course, for the most popular interfaces on the market, it's better to use, it makes sense to use digital isolators with default output high. Because those interfaces have a high logic level in standby mode, idle mode. It means less power consumption because the internal modulator of high frequency signals is not operating during standby mode. And speaking about digital isolators with default output low, it makes sense to use them in switch mode power supplies to isolate gate drivers from microcontrollers for safety reasons, and also it makes sense to use them in SPI and CAN interfaces in case there are low in standby. Again, because of power consumption. As can be seen, the current consumption of the digital isolators is related to the default output state. Usually, in datasheet, the current consumption of digital isolated is specified in default output mode when internal modulator of high-frequency signals does not operate. and in non-default output mode, when internal modulator of high-frequency signals operates constantly. We can call these modes static consumption or DC mode. Obviously, the current consumption in default output mode will be lower than in non-default output mode. In this table, you can see current consumption for two-channel Würth Elektronik digital isolator, and in default mode, you can see that current consumption or power consumption is 2 times lower than in non-default mode. And the technical specifications also provide dynamic current consumption values that depends on the data rate transfer. And again, in this part of the table, you can see current consumption for different data rate. We specify in our datasheets current consumption for 1 megabit per second, 10 megabit per second, and 100 megabit per second. And again, for higher data rate, current consumption will be higher. You can compare it to 1 megabit per second, and the difference will be approximately 5 times. Okay, and the last property, and I would say the very important, maybe one of the most important property of digital isolators. This is common mode transient immunity, or CMTI. And this is a device ability to withstand fast changes in voltage between its input and output grounds without errors. On this picture, you can see a SMTI test schematic, and during the SMTI test, a pulsed transient is applied across the isolated ground planes, ground 1 and ground 2. You can see it here, ground 1 and ground 2. A digital signal is sent to the inputs, and the outputs of the isolator are monitored for data distortion. This is particularly important for high-speed data transmission. And of course, main benefits of a high CMTI level, it will be signal integrity, because it maintains data reliability even in fast-changing voltage environments. Then its noise immunity resists AMI and electrical noise, preventing errors. Then system stability ensures safety and stability in high-voltage system. High-speed compatibility supports high-speed data without mistakes. And extended application range suitable for harsh environment with strong magnetic fields and overvoltage applications like motor control and automation. And last, longer life and reliability. It means reducing stress on internal components, resulting in increased reliability and longer life in challenging environments. And Würth Elektronik digital isolators offer a CMTI level of 150 kilowatt per microsecond. This is a very high level of CMTI. Now, as you can see, we come back to application slides. Why? Because now we know the most important, the most critical properties of digital isolators, and we can say that digital isolators are very reliable solution for galvanically isolation of high speed signals. Especially we can use it in harsh environment too, like for example industrial automation. Now my last part. Let's speak about Würth Elektronik portfolio, but first I would like to introduce you our new board. The work is still in progress, but it will be the board based on isolated RS485 interface. You can see this board on the slide. And this board is optimized for 10 megabit per second data rate and 10 meters cable length. As also you can see that input voltage will be between 315 and 5.5 volts, output voltage 3.3 volt, and isolation voltage up 5000 volt RMS according to UL 1577 standard, and as I already said, data rate up to 10 megabit per second. On the right side of the board you can see line filter and half duplex RS485 transceiver. Then in the middle of the board you can see digital isolator, 4-channel digital isolator with integrated DC-DC converter. Then we can see input filter for isolated DC-DC converters, and a few connectors. This connector for power supply of digital isolator, and this connector for high frequency signals. Okay, you can see here our portfolio, part of our portfolio, because we have 4-channel digital isolators with integrated DC-DC converter. These products have isolation voltage up to 5000 volts according to UL 1577 standard, and also provide reinforced isolation according to VDE or IC standards. The data rate for this product 100 megabit per second. We have 6 part numbers, and each part number has an evaluation board available for each part number. Then you can see digital isolators without integrated DC-DC converter. On the slide you can see 2-channel digital isolators in SOIC 8 narrow body package that provide isolation voltage up to 3.75 kilovolt, and also they provide basic isolation. Then you can see 2-channel and digital isolators in SOIC 8 wide body package, and 4-channel digital isolators in SOIC 16 wide body package. Those products provide isolation voltage up to 5000 volt RMS according to UL 1577 standard, and also provide reinforced isolation according to VDE certificates. All unpowered digital isolators provide data rate up to 150 megabit per second. And as I already said, all products provide CMTI level 150 kilowatt per microsecond. Okay, this is my last slide. Thank you so much for your attention, and if you have questions, please let me know.
Yeah, thank you, Artem, for your interesting presentation. Now we will come to your questions. Before we start with the Q&A session, I will share the handout, and now you can download. Okay, then I would say we start with the first question. First question. You specified the EMI measurement for 2-layer board without Y capacitor. Did you measure radiated emission for a 2-layer board with external Y capacitor?
Thank you, Silas, but to be honest, it's very good question, because yes, we tested and designed 2 boards, 2 layers, 2 types of boards with 2 layers, and one of them was with external Y capacitor, and one of them was without. And the board with external Y capacitor, let's say, when we're speaking about radiation emission, shows better results, but still not enough to pass the test. That's why we recommended to use 4 layers boards, 4 layers design, instead of 2 layers. Yeah.
Okay, thank you. Then, next question. What is the topology of integrated DC-DC converter? What frequency does it operate at?
Okay. Let's say primary side is full bridge topology. Then goes a high frequency transformer, and secondary side is again a full bridge topology. and operating frequency for integrated DC-DC converter will be around 13 megahertz. You can find this information in our datasheet. Yeah.
Thank you. Okay, then I would say one last question. When will more detailed information about isolated RS485 design example be available?
As I already said, we're still working on this board, but I hope all related documents will be available until the end of this year. And I also would like to say that we also are going to design other boards based on the most popular isolated interfaces on the market, for example, for SPI and for CAN2. But I think information about these boards will be available later, I think next year. Yeah.
Okay, thank you. Then I would say we come to the end of the webinar today. Thank you for your attention. I hope you enjoyed it. Thank you, Artem, for your interesting presentation and for all the answers. And now I hopefully we see us on our next webinar. Thank you and goodbye.
Thank you so much. Have a nice day.